The dissipation of dark, storm clouds. A comprehensive analysis. Introduction. The sky's transformation from dark, foreboding storm clouds to clear blue is a phenomenon that has fascinated humans for centuries. This process, known as cloud dissipation, involves a complex interplay of atmospheric conditions and physical processes. Understanding why and how dark storm clouds dissipate requires a deep dive into meteorology, including the dynamics of cloud formation, the role of moisture and temperature, and the impact of various atmospheric forces. Cloud formation and types. To comprehend cloud dissipation, it's essential first to understand how clouds form. Clouds are visible masses of tiny water droplets or ice crystals suspended in the atmosphere. They form when moist air rises, cools, and condenses around small particles like dust, pollen, or sea salt. Types of clouds. Cumulus, fluffy, white clouds, often seen on clear days. Stratus, layered clouds that cover the sky, leading to overcast conditions. Cumulonimbus, towering storm clouds associated with thunderstorms. Cirrus, high wispy clouds made of ice crystals. Dark storm clouds, primarily cumulonimbus clouds, are associated with severe weather conditions like thunderstorms, heavy rain, and even tornadoes. These clouds form under specific conditions that involve substantial atmospheric instability. Atmospheric conditions leading to storm clouds. Moisture and humidity. Storm clouds require a significant amount of moisture. Warm, moist air rises and cools as it ascends, reaching a point where the air can no longer hold all the water vapor, leading to condensation and cloud formation. Temperature and pressure. The atmosphere's temperature and pressure profiles are crucial. Rising warm air meets cooler air at higher altitudes, leading to the cooling and condensation of water vapor. Low-pressure systems typically facilitate the rising motion needed for storm cloud development. Atmospheric instability. For storm clouds to form, the atmosphere must be unstable. This instability is often measured using the lapse rate, which is the rate of temperature decrease with altitude. When the lapse rate is steep, the atmosphere is more unstable, encouraging the upward motion of air parcels and cloud formation. Lifting mechanisms. Several mechanisms can lift air to the point where it cools and condenses into clouds, including convection. Warm air rises due to surface heating. Orographic lifting. Air is forced to rise over mountains. Frontal lifting. Air is lifted as different air masses meet. Convergence. Air flows together from different directions and rises. Dissipation of storm clouds. The dissipation of storm clouds involves reversing or counteracting the conditions that led to their formation. Key factors contributing to this process include changes in moisture levels, temperature profiles, atmospheric stability, and lifting mechanisms. Moisture depletion. As precipitation falls from the storm clouds, the amount of moisture in the cloud decreases. This reduction in water vapor can lead to the gradual thinning and eventual dissipation of the cloud. Additionally, the downdrafts within the storm can bring drier air into the cloud, further reducing its moisture content. Temperature changes. As the storm progresses, the temperature profile of the atmosphere can change. If the upper atmosphere warms or the surface cools, the temperature gradient that supports the upward motion of air parcels can weaken. This change can stabilize the atmosphere, reducing the upward motion necessary for cloud maintenance. Increased atmospheric stability. The dissipation of storm clouds is often associated with increased atmospheric stability. This stability can occur due to several factors. Warming of the upper atmosphere. This can happen due to the advection of warm air aloft or latent heat release during condensation. Cooling of the surface. This can result from rain-cooled air or nighttime cooling. Subsidence. The sinking motion of air, often associated with high-pressure systems, can suppress cloud formation and lead to the dissipation of existing clouds. Lifting mechanism cessation. The lifting mechanisms that initially formed the clouds can weaken or cease. For example, the passage of a front can lead to a decrease in frontal lifting, or surface heating can diminish as the sun sets, reducing convective lifting. Physical processes in cloud dissipation. Several physical processes contribute to the dissipation of storm clouds, including evaporation. When the air surrounding the cloud is relatively dry, evaporation can occur at the edges of the cloud. This process reduces the cloud's size and contributes to its dissipation. Evaporation is particularly effective when the air's relative humidity is low, allowing for the rapid uptake of water vapor. Mixing and entrainment. The mixing of drier air from outside the cloud with the moist air within the cloud entrainment can lead to the dilution of the cloud. This process can weaken the cloud by reducing the concentration of water droplets or ice crystals, leading to a reduction in cloud opacity and eventual dissipation. Precipitation. The formation and falling of precipitation remove moisture from the cloud. As rain or snow falls, the cloud's water content decreases, leading to a reduction in size and density. The downdrafts associated with precipitation can also bring drier air into the cloud, accelerating the dissipation process. Radiative cooling. Clouds radiate heat to space, leading to cooling. At night, when solar heating is absent, radiative cooling becomes more significant. This cooling can stabilize the lower atmosphere, reducing the buoyancy of air parcels and leading to cloud dissipation. Case studies and observations. Dissipation after frontal passage. When a cold front passes, it often leads to the dissipation of storm clouds. As the cold, dry air behind the front moves in, it can stabilize the atmosphere and reduce the moisture available for cloud formation. Observations often show a clearing of the sky following the passage of a cold front. Diurnal variations. Storm clouds that form due to daytime heating often dissipate in the evening. As the sun sets, surface temperatures decrease, reducing the convective lifting that supports cloud formation. This process is commonly observed in summer thunderstorms, which can quickly dissipate after sunset. Subsidence and high-pressure systems. High-pressure systems are associated with sinking air, subsidence, which suppresses cloud formation. When a high-pressure system moves into an area with storm clouds, the subsiding air can lead to the dissipation of the clouds. Satellite observations frequently show a reduction in cloud cover under high-pressure systems. The role of advanced technology in studying cloud dissipation. Modern technology has significantly advanced our understanding of cloud dissipation. Tools such as satellites, weather radars, and numerical models provide detailed observations and simulations of atmospheric processes. Satellites. Weather satellites provide continuous, global observations of clouds. They can monitor the formation, development, and dissipation of storm clouds in real time. Instruments on satellites can measure various properties of clouds, such as their temperature, moisture content, and vertical structure. Weather radars. Radars provide detailed observations of precipitation and cloud dynamics. They can track the movement of storm clouds, measure rainfall rates, and observe the internal structure of clouds. Doppler radar, in particular, can detect the motion of air within clouds, providing insights into the processes leading to dissipation. Numerical models. Advanced numerical weather prediction models simulate the atmosphere's behavior, including cloud formation and dissipation. These models use mathematical equations to represent physical processes and can provide detailed forecasts of cloud development. High-resolution models can capture small-scale processes that are crucial for understanding cloud dynamics. Challenges and future directions. Despite significant advances, several challenges remain in fully understanding and predicting cloud dissipation. These include microphysical processes. The detailed processes of condensation, evaporation, and precipitation at the microscale are complex and not fully understood. Improving our knowledge of these processes is crucial for better predictions. Interactions with aerosols. Aerosols, tiny particles in the atmosphere, play a significant role in cloud formation and dissipation. Understanding the interactions between aerosols and clouds is an active area of research. Climate change. As the climate changes, the behavior of clouds is also changing. Understanding how cloud formation and dissipation processes are affected by global warming is essential for accurate climate predictions. Observational limitations. While technology has advanced, there are still limitations in observing clouds, especially in remote or data-sparse regions. Improving observational networks and developing new technologies are ongoing challenges. Data assimilation. integrating diverse observational data into numerical models, data assimilation, is a complex task. Improving these techniques can enhance model accuracy and lead to better predictions of cloud behavior. Conclusion. The dissipation of dark, storm clouds is a complex and multifaceted process involving various atmospheric conditions and physical mechanisms. Understanding why and how these clouds dissipate requires a deep knowledge of meteorology, including the dynamics of cloud formation, the role of moisture and temperature, and the impact of atmospheric stability. Advances in technology, such as satellites, radars, and numerical models, have significantly improved our understanding, but challenges remain. Future research and technological developments will continue to enhance our ability to predict and understand this fascinating atmospheric phenomenon.